Bismillahirrahmanirrahim. Welcome back. In today's video, we will discuss Karnaugh map and implementation of Karnaugh map for the minimization of Boolean expressions and implementing it in Quartus as well as in Proteus. So now let us first discuss its basic theory, that what is Karnaugh map and why do we need a Karnaugh map. A Karnaugh map is a pictorial method used to minimize Boolean expressions without having to use Boolean algebra theorems and equation manipulations. So two things. What is a Karnaugh map? It is a pictorial method. And why do we need a Karnaugh map? Is that we have to skip the method of Boolean algebra theorems and equation manipulation, because in DLD we have this method of equation manipulation using this different Boolean algebra theorems, and that is a bit complex method, which will lead to a big mistake if any small error occurs. Now, a K-map can be thought of as a special version of a truth table. How do we say that? In Karnaugh map, uh, in Karnaugh map method, basically, it is a method of minimization. How do we minimize a particular Boolean expression? You can see it in a very, it is very early to show you this, but you have to understand the definition. This is a Boolean expression that is not being minimized. Now using this K-map, I have minimized this Boolean expression to this. So we see that this is a Boolean expression of mm, sum of seven minterms, and here is a sum of four minterms. Okay, now for K-map we need a truth table. From truth table we basically identify on which output there we get a high. Okay, these are the steps. Number one, we make a truth table. As I have made a truth table, I had a function f, and that function was got from four different inputs. We will see why we uh, took four inputs. So basic thing is we have a function that is obtained from four inputs, and those that function have different high outputs. We will take those high outputs and fill a, a table like this. So number one is two variable map, in which we have two inputs. So in two variable map we have a um, four box of table. In that, one must be uh, a bar or b bar or anything, or x bar. The other must be a. One must be b bar and the other must be b. So we get a low here and a high here. So filling that, the method of filling that boxes is where the point where we got high, we fill that that cell. Now let's skip this explanation and go to three variable K-map table. If we have a three input function, that function, from that function we get different high and low outputs. Now how to make that three variable K-map. The method is we put one variable in a column or in a row. Okay, and the other is 4. It means 2 to 4. It gives us a 3 variable k map. So how we label these rows is 0 0 1 0 1 1 and 0 1. That is important, that this sequence must not be changed. 0 0 1 0 1 1 and 1 0. Now filling that is easy. It is from the truth table. We just have to put the ones where it comes. Okay, coming to the main variable, 4 variable map that we have to implement in this lab. So in a 4 variable map, we get we have a 4 variable input and a single output. Now the same method, we get a high in some outputs. So we fill that high in our boxes. Now you must remember that this will also follow the same rule, that the first one will be 0 0, the other will be 0 1, then 1 1 and then 1 0. Same in rows, 0 0 0 1 1 1 and 1 0. Now we learned that how to fill a k-map from its table, from its truth table. Now we have certain rules in k-map. The rules are that we need not to include zeros uh, while we while we making a group to minimize it. Wherever one will come, it in two variable k-map, we get a group of 2. That is maximum, obviously. Wherever we get a group of 2, we highlight it and write it in a minimized expression. Now we can have a group of 3, and it will be it should not be diagonal. It should either be vertical or horizontal. So it is not a group of 3, it is a group of 2 from row and group of 2 from column. Now we cannot have group of 3. Remember that grouping can be done only in a power of 2. Means that it should be 2 power 1, 2 power 2, 2 power 3. It means it should be 2 4 8 16. Okay, now that was about grouping. Now grouping can be 2, grouping can be 4. It can be in a line, it can be in a row, it can be in a column. That doesn't matter. It can also be from the edge points. It means if it is one hair, it is one hair, one hair and one hair, then we can have a group of 4 like that. Okay, remember one thing, that two groups can overlap each other, but only if it is needed. It means that if one is remaining, one high is remaining and the other has already occupied, then we can make a group with already occupied high with that non-occupied to make a group. I was talking about that we can have a group in edged cells. Okay, so now we have the task of making a 4 variable k-map. For that we have 4 inputs, a function. So this function have high on 0 1 and different outputs. Now from this truth table we can use to write our required expression, boolean expression. Now this is basically sum of minterms. These are the minterms. We used minterms to in order to represent this output here. A bar, B bar, C bar, and D bar. All are zeros. We will discuss the concept of minterms in coming video. So let's move to K-map. We have discussed how to fill this table, and it will be a 4 cross 4 boxes in which each cell that will be the output that will be high, according to its address, it will be filled as high. So how to find the address? Basically, it is a bit tricky task. The first row is 0 0 and the first column is 0 0. It will be a 0 0 0 0. It will be the first one, the 0. 1 will be here, 2 will be here, and 3 will be here. We have already discussed this, that this is a predefined concept, or it is a law to make this K-map, is that the first one be 0 0, the other should be 0 1 1 1 and 1 0. Okay, now this second row noted as 4 5 7 and 6. We will see it from a typical K-map of 4 variable. So the cells are denoted as 0 1 3 2 4 5 7 6. Then we skip this one, then 8 9 11 10, and then come back to this and denote it as 12 13 15 14. So I think you have got the idea of how to label the columns, rows, and each cell in a 4 cross 4 or 4 variable K-map. Now using that addresses, you can fill this K-map easily. Now from here, where there is a high, we can make a group of 2 or 4 or 8. In our K-map, we just have encountered group of 2. The first group is this one. Second group is this one, and the third group is this one. Fourth group is this one. So we have a 4 groups. So we predict that there should be a sum of 4 minterms. That's our prediction. Now let's see what are the addresses. The address of this one is 0000. Address of this one is 0001. Now how to write it in a single expression? It is the bit from A B C D, the bit that is not changing will come in the minterm. Like in this group, moving from one cell to other, this A and B both does not change. Like in this columns, from moving from this to this D changes. It is 0 in the first cell and it is 1 in the second cell. So we have 3 bits that do not change. It's A, B, and C. So A bar, B bar, C bar, this will come in our first minterm for this group first. Now let's see the second group, this and this. The address of this is 0110 and this one is 1110. So writing it in a single minterm, it will be that both C and D bar does not C and D bar do not change, and here A bar A bar B. So A bar changes from 0 to 1 and B remains the same. So the C D bar and B, it means that B C D bar, this will come for group 2. Now for this expression, for this group, we write, uh, since this B changes from 1 to 0, so A will come, C and D bar will come. So it will be A C D bar, A C D bar, this one A C D bar. Now for the group, this one, the second group, we see that A and B bar do not change, but here C bar changes, sorry, D bar changes from 0 to 1. So we will say A B bar C bar, A B bar C bar. So this was uh, the theory of K-map. Now let's implement this in Proteus. Implementation is same, but the same that we have implemented in previous videos. The first one is implementation of this whole expression, this non-minimized, the original Boolean expression. So we have uh, seven expressions in sum. So for sum we use an OR gate. We'll use an OR gate with 7 inputs. Okay, and we have 7 different AND gates, because these are in product. So we will use 7 different AND gates, each having 4 inputs, giving them a high and a low according to this expression for each gate. Okay, we will get this circuit. Now after implementation of this original expression, we will implement this minimized function, and we will see that it has minimized this whole circuit of 7 AND gates and 1 OR gate. We have minimized it to 4 AND gates and a single OR gate. Now how to implement it? It is same, using an OR gate of 4 inputs and in 4 different AND gates of 3 inputs. That's it. Now after simulation, you will see that both of them gives us, sorry, the Proteus is not responding. We see that we get a low from both the circuits. So this combination gives us low for these expressions. Okay, after Proteus we will move to Quartus. In Quartus we have already compiled it, and everything is ready. For the purpose of writing code for it, I have used gate level implementation. So in gate level implementation, I have used these different gates: 1, 2, 3, 4, 5, 6, 7 gates and 1 OR gate according to our Proteus requirement from here. And for the A bar, B bar, C bar, D bar, I have assigned these variables the values of A bar, B bar, C bar, and D bar, because we needed the the lows the opposite of these inputs also in our implementation. So this is all about the code. We have already compiled it. Now from the RTL viewer, we will confirm our code, that since it gives us 7 different gates and in OR gate and from 4 inputs and NOTs, we can confirm it that it has correctly we have correctly made our code and implemented it in Quartus. Now let us see its simulation. Its simulation is we have given the inputs high and sorry waveform different waveforms, and we have got this signal in the output. Now we will compare this signal with our minimized signal, that we should get the same signal from that too, in order to confirm that we have successfully and correctly used K-map in order to minimize our logic circuits, logic expression. So now after opening and compiling and getting ready the minimized the code for minimized expression, Boolean expression, we used the assign implementation for assign logic implementation for implementing this minimized Boolean expression. Now let's see its RTL viewer. Does it confirms the get implementation? Yes, because it has the same implementation as we have seen in Proteus. Now let's see simulation. Does it confirms that both the implementations are same, the original one and the minimized one. So this is the waveform of minimized, and this is the waveform of the original one. So we see no difference in both. So this confirms that um, we have correctly minimized this function to this function using K-map. So this was our today's lab, in which we have used the method of K-map in order to minimize this original expression to a small a minimized expression. That is it for now. Thank you all. See you again. Allah Hafiz.